Welcome to Cap 3. This is section 14.1 on line integrals. So a line integral is the area under a curve in 3 dimensions. So if we let C be a curve in 3 dimensions along a surface, we can think of a line integral as kind of the area of the curtain that's formed underneath that curve. So if we have some curve along the surface here, this is our curve C, then that curve, the line integral, gives the area underneath that curtain. So we indicate the line integral as the integral C, or the integral over the function C, of the surface f of s ds, where s is the arc length parameter. If C is a closed curve, we indicate this with a little circle around our integral as our closed integral. Again, with f of s ds. Remember that the arc length parameter is a special sort of time clicking along. So the arc length parameter is when we take one step in time, we go exactly 1 unit along the curve. And so we'd like to be able to adjust for that, and so we don't have to keep track of exactly the arc length parameter. So we have some properties of line integrals. So namely, if we have a scalar times 2 surfaces, or if we can break our curve along 2 surfaces where we have a scalar times 1 surface plus a scalar times another surface, we can break that across just like we could in Calc 1. We could break that integral up into 2 pieces. We have the first scalar times surface, the line integral along the first surface, plus a second scalar times the line integral on the second surface. The K1 and K2 are scalars, and F and G are 2 different surfaces. If we break our curve up into 2 pieces, let's say C1 and C2, and the curve C is formed by traversing C1 and then C2, or C2 and then C1, you can piece together multiple curves. We can take the line integral over the curve C and break it into portions. This is equivalent to in Calc 1 when we broke up regions of integration into smaller, easier to calculate regions. So if we have a curve parameterized by a function, r of t, a vector valued function, given by g of t and h of t for some time a to b, and some surface z equals a function x and y, of x and y, then our line integral here, the integral over the curve C of f of s ds, we could rewrite that as a function of time, where our time varies from a to b of the surface parameterized by g and h. So our x value is turned as a function of time g, and our y value is a function of time h, times the derivative of the parameterization curve, magnitude of that vector, dt. So this should look familiar. This piece here should look like what we came up with arc length. This is where we derived an arc length formula before. So this should be familiar background. The idea here is that along our surface, this is our path along our surface. And that's the difference between what we did in arc length parameter earlier in this semester with now we're looking at the path along the surface as kind of a weighting factor for our parameter. And so in shorthand notation, we can take the surface, insert the curve, and then dot it with the magnitude of the vector valued function. It's important to note that the magnitude of the vector, the velocity vector, may not be a constant, that it most likely will be a function of time. So there's 4 basic steps. So you want to first parameterize your curve C as a function of time if it's not already. This is equivalent to finding the vector valued curve R of t. Secondly, find your velocity vector and its magnitude. And then again, note that most likely the magnitude vector will, or the magnitude scale will most likely not be constant. It will be a function of time. And then plug into your pieces into your line integral and then solve. Sometimes this is easy, but oftentimes you will need some technology to solve it. So let's look at an example here. So let's let C be the portion of the curve along the line y equals 3x plus 2 on the interval x equals 1 to 2, and the surface is f of xy equals 5x plus 2y. And we want to find the area under the curve under the surface f. So the first thing we need to do is parameterize our function. So let's let x equal t. So the easiest parameterization is often to let x equal t or y equal t. So if we make this the case, then y equals 3t plus 2. So this means that our vector valued function for our curve is t, 3t plus 2. And the interval t is a value from 1 to 2 because that's our x interval from 1 to 2. So r prime is equal to the value 1, the vector of 1, 3. So the magnitude of r prime is equal to the square root of 1 plus 9, which is the square root of 10. So this is steps 1 and 2. Steps 3, we would plug in our pieces. So 1 and 2, the curve f of r times the magnitude of r prime dt, this is equal to 1 to 2. We plug in our function x and y, so we get 5t. T is our x value, plus 2 times our y value, which is 3t plus 2. Close that parentheses, times our magnitude, which is square root 10 dt. So simplifying this, this becomes 1 to 2. Let's pull out the square root 10 out front. Since it's a scalar, we can pull it all the way out front. So we have 11t plus 4 dt. And this is a simple problem to solve. We can see that this is square root of 10 times 11 halves t squared plus 4t evaluated from 1 to 2. This is square root of 10 times 22 plus 8 minus square root of 10 times 11 halves plus 4. So we can simplify this and we get square root of 10. The 8 minus 4 plus 22 gives us 26 minus 11 halves. And so this would be the area underneath the surface along that curve. So if we think about dropping a curtain along that curve, that's our area. So let's do another example here. So let's set up the integral, but not solving the line integral for the portion of the curve along this parabola, 2x squared plus x plus 1 over x equals 0 to 1 along this surface x squared plus 2y. So again, step 1 is to set up our r vector. Let's let t be x. So then our y value is 2t squared plus t plus 1. Step 2, so r prime is equal to 1 for t plus 1. The magnitude of r prime is equal to the square root of 1 squared plus 4t plus 1 squared, which we can simplify this, and we get 1 plus 16t squared plus 8t plus 1, or the square root of 16t squared plus 8t plus 2. Rewrite that down here, 16t squared plus 8t plus 2. And so then we plug in our pieces. So we get the integral from 0 to 1. Our function is t squared plus 4t squared plus 2t plus 2. So substituting the t into each the x and the 2t squared plus t plus 1 into the 2. And so that is our f function. And then multiplying it by the square root of 16t squared plus 8t plus 2. And then our dt on the end. So this is, we've set up our function. So we've got x squared, which is our x is our t, plus 2y, so 2 times our y piece here. And then our magnitude of r prime. So again, here we have our magnitude of r prime, which is a function of time and not a constant. So we've set up our function here. You can combine this to get 5t squared plus 2t plus 2 if you'd like. So as you solve this, we see that This is not a nice u substitution. It doesn't look very nice for trig problems that we know. And so this would be the use of technology here to solve this most likely. So the next video will have a couple more examples of how to start setting up line integrals and solving basic line integrals. As always, if you have questions, let me know.